Hello everyone, I am Istiak. Today I am presenting my project on predicting and verifying cyber sickness in virtual reality. Uh, the project is inspired by a recently published paper which is probabilistic verification of cyber sickness in virtual reality through Bayesian networks. So this is the outline for today's presentation. First, I will start with a short introduction and the motivation behind this work. Then I will discuss about the methodology and implementation details. Then I will show the result and I will also compare our result with the baseline paper. Then I will talk about the limitation and future directions, and after that I also added some STL properties which I am planning I gonna add in future work. I will also show this STL property, and finally I will wrap up with some key conclusion. Okay, so as we all know that virtual reality is rapidly expanding beyond gaming into critical fields like education, healthcare, and also military training. However, this growth faces a major safety barrier, and which is known as cyber sickness. Uh, the symptoms uh, include like nausea, disorientation, and eye strains. And also, these phenomenon affect nearly 80% of users. To address this, although researchers has started using different kind of ML and DL models to predict when sickness occurs, but the problem is that they make prediction but cannot provide formal safety guarantees. So in high stakes environment like defense training, uh, and also surgical training, this lack of certainty is unacceptable. So to addressing this gap is the core motivation for this project. Additionally, recent research has shown that combining Bayesian network with dice verification addresses this gap. So in this project, I implemented this approach. So initially, I implemented a Bayesian network to predict cyber sickness from available system and physiological data, and then I use dice for formal probabilistic verification to ensure safety guarantees. Okay, so the methodology I implemented comes from the paper. I already said that, which is probabilistic verification of cyber sickness in virtual reality through Bayesian network. So the paper proposed a complete framework with three main components, as you can show in this architectural diagram. So first, directed acyclic graph. It proposed using a hierarchical Bayesian network to model the causal change where system parameters like luminance and motion complexity influence physiological responses like heart rate, galvanic screen galvanic skin ratio, pupil diameters, and which is turn determine cyber sickness severity. And the second one is structural learning. So to automatically discover which variable causally influence which, the framework use hill climbing algorithm with uh, bias scoring and hierarchical constraints to ensure the learned structure aligned with the domain knowledge. And and third, formal verification using dice. So crucially it incorporate dice, a formal probabilistic verification tools to compute exact probabilistic and provide mathematical rigorous safety guarantees. So in this project, I implemented all those components from scratch and validated those that the learned structure working properly and following formal safety properties. For this work, I used the same publicly available VR working dataset that the baseline paper used, but they also added some additional features like spectral entropy, luminance, Hawk features, and so on. So the paper used total 22 features, uh, where 10 was system parameters and 11 were physiological signals. However, their updated dataset is not publicly available till now. So for this project, I selected the most 10 most informative features available in the public dataset. One is system parameter. I take this as a motion intensity, and 8 physiological signal like heart rate, HRV, and so on. So importantly, uh, when once the full data set is released, we can simply retain the model with the complete feature set. Okay, so the implementations follows a structure five-stage pipelines, each captured in a separate notebooks. So all pre-processing and training steps are fully automated and reproducible. So initially, I start with the 77 raw sensor features from VR working dataset and applied information gain filtering to identify the most important features. Then I discretize all continuous features into five beans as Bayesian network required categorical data for structural learning. Then, followed by the baseline paper, I use hill climbing algorithm with bias scoring and hierarchical constraint to train the BN model, and it discovered 12 casual edges, uh, showing how system parameter influence physiological response, which in turn determines cyber sickness. As you can see in the right image, an example image for Bayesian network structure. And for evaluation, I validate the model using 5-4 cross validation. And finally, I added DICE formal probabilistic programming language to verify the model. As I discussed earlier, to evaluate the trained Bayesian network, I use 5-4 cross validation. As we can see in the right top, my exact accuracy is 62.96%, which actually pretty much similar to the original paper 62.12%. Even though I use only 10 features compared to their 21, this provides my feature selection was highly effective. And for extended accuracy, which accept being off by just one level, I achieve 76%, while this is slightly below to paper's 83%. It is still a strong result given to the reduced data. As we can see in the confusion matrix in the bottom right, while the exact accuracy has some noise, the extended accuracy matrix on the right confirm that when I group nearby levels, the model perform much better. This suggests that the model struggles to distinguish between specific adjacent levels, but it generally effective at identifying the category of cyber sickness. Ultimately, I replicate the paper core performance with the half the data and validate that implemented model is both robust and efficient. Okay. Uh, to formally verify the model, I encode the learn VN structure into dice code, which then execute in a Docker container to ensure reproducibility and consistency. And these are publicly available in this link, as you can see in the bottom right. Uh, then I perform total four type of verification test. First, checking the baseline distribution with no condition. I get 40% risks, which matches with the baseline exactly. Second, the high stress scenario shows 60% risk versus their 80.6%. This difference is expected as I use a reduced feature set. So we capture fewer risk factors, but the direction is identical. Both models increase risk under stress. And third, verifying formal property like monotonicity and probability bounds that that matters for implementation validation. Monotonicity is verified in both the model, baseline and our, and and we and and high stress, and we got that high stress increase the higher risks in both the our and the paper model. And when the stress is low, then the risk is also low. So the direction is almost same, and they follow the same pattern. And fourth, testing realistic VR scenario with different combination of stress factors. I got that uh, risks stay at 45% with natural condition and rises to 60% during stress test, as you can see in the second picture in the right side. Okay, so although Bayesian network and DICE gives us a formal verification, but we identify four critical limitations. First, no temporal reasoning. We can say that what's the probability of cyber sickness right now by using Bayesian and DICE. But now, but the problem is, what if GSR stays high for 5 minutes? So BNN dies not able to answer those type of questions. Second, offline only. So no monitoring during actual VR session. So ultimately the users are not protected. Third, limited accuracy. Uh, since the features prone 87% of features and achieve only 62% accuracy because Bayesian network complexity is exponential. Fourth, scalability. We cannot use better predictors like deep learning because dice require explicit probability tables. Those limitation motivates us to explore signal temporal logic for runtime temporal verification. So the core innovation is moving from offline to online. What STL can enable, since STL are able to express temporal properties, for example, sustain, safety, response deadline, event sequence that Bayesian network cannot do. So it also will provide a response guarantee, real-time monitoring, and STL is also model agnostic. So we can use any model, for example, LSTM, instead of being locked to the Bayesian network. And the lastly, it will provide scalability. So those are the six example properties I'm planning to add in my future work. As we know that Bayesian network and dice are not able to give the system verification. It only give you model verification. But STL enable both two level of verification, that one is model verification and another one is system verification. So as we can see in the right side, model verification verify the predictor's behavior like stability, monotonicity, and lead time. And the right side, as we can see that system property verify actual runtime safety, like user physiological stay safe or not, system response in time, and rendering system and rendering stay smooth or not. Together, those six property create a complete safety picture. The model is trustworthy, and the system protects user in real time. To conclude, I implemented the complete Bayesian network and dice pipeline from scratch using structural learning, feature selection, and formal verification. And train model discovered 12 causal relationship and formally verified monotonicity, probability bound, and causal structure. Our baseline model got 45% severe cyber sickness risks and increased to 60% under high stress, which is consistent with the baseline paper. This implementation basically demonstrate the feasibility of formal verification and also provide the baseline for future safety approaches. Those are the reference used for today's presentation. Thank you everyone. I'm happy to take any questions.